So I wanted to make a short video that is going to look very similar to the kinds of questions you're going to see on your quiz. Go through it fairly slowly, kind of walk through a thought process if you're kind of not quite sure how to start a problem like this, to help you hopefully prepare for the in-person quiz. Okay, so here's the question. Imagine you've taken an ice cube, and I tell you the mass of the ice cube, out of your freezer, and your freezer is at minus 20 degrees C, and you're going to let it sit out until it's reached room temperature at 25 degrees. So I want to know how much heat must have been added to complete this process. So again, you don't need pictures for things. I often draw pictures because it helps me conceptualize what's going on. So first, let's imagine we've got an ice cube here, and our ice cube is 22.67 grams. It's at minus 20 degrees C. And the first thing that's going to happen is I'm going to add heat that's going to basically take that to an ice cube that's at 0 degrees. Right, so I've got this ice cube here that's still going to be 22.67 degrees, but now it's going to be at 0 degrees. And how do I know I stop with an ice cube at 0 degrees? Because I know at 0 degrees, that's when that ice cube is going to start to melt. So at this point, any heat that I provide is going to be heat that allows me to melt, okay? And then I'm basically going to have a puddle of water here. Okay, so this is going to be a puddle of water that's still going to be 22.67 grams of water at 0 degrees C, but now this is liquid. And now the last thing that happens, okay, is I'm basically going to be continuing to add heat because I want to have this pile of water now, 22.67 grams of water, be at 25 degrees C. Now, a couple of things here. This practice problem, as you're going to see here, because I've drawn 3 arrows here, is a 3-leg problem. Remember, you're not going to see something that is 3 legs, but you're going to see something that's 2 or maybe just 1 leg, and you need to be able to determine how many legs you have. Okay, so this is going to be a little bit longer in terms of the calculations that you're going to do, but it's the scope of the kind of problem you're likely to see. So what I want to highlight here is what's going on. Well, when I have my ice cube here, this is going to be a solid that's at minus 20 degrees, and this is going to be a solid at 0 degrees. So what's happening during this arrow is I'm increasing the temperature, so I'm changing the temperature, and I'm staying at the same phase. Now what happens in this next transition is I am keeping the same temperature. So this is same temperature, and I'm going to be changing phases. Oops, changing. Remember, a triangle is a delta that stands for change. Change phase. I'm actually just going to change this right here so I can keep this formalism kind of the same here. Let's use a delta. So we're delta T, we're changing the temperature same phase, and then we're going to be same temperature change phase. And then once I have that puddle of water, then I'm going to be, again, changing temperature same phase. So big picture here is what's happening is I'm never doing 2 things at the same time. I'm either choosing to have my heat change my temperature or change my phase. Now, one of the things you'll notice is that these come in 2 flavors. I'm changing temperature, same phase, okay? And then I'm going to have changing phase, same temperature. Each one of those represents a different kind of calculation. So let's go over here and let's draw a heating and cooling curve. Now at this point, there's nothing that I'm doing right now that's required for your quiz. The idea is that you probably are able to see some of this in your head to understand the kinds of calculations that you do. But let's kind of map this on here. Remember, temperature is always going to be on my x-axis or on my y-axis here. Heat added or removed if you're cooling something is going to be on your x-axis. So I'm going to start out at minus 20. I'm going to have a temperature change until I hit 0 degrees, and then I'm going to change temperature again until I get to 25 degrees. So what's going to happen, I'm going to draw some lines here. I'm going to increase my temperature until I hit 0, and then any heat that's added is going to keep the same temperature, and then I'm going to increase again to 25. So there's my 3 legs here. So again, let's highlight what's happening here. Here I'm increasing the temperature of a solid, and then I'm melting a solid, and then I'm increasing the temperature of a liquid. Okay, so those again map onto the different kinds of calculations. So these ones that I'm boxing in red here are changing the temperature but keeping the phase the same. What I've got highlighted in green here is where I'm doing a phase change, keeping the temperature constant but changing the phase. Now, what we need to be able to do here is recognize the different kinds of calculations that we have for each of these phases. If I have a line that looks like this, where I'm changing the temperature but keeping the phase the same, the calculation that I'm going to use is going to be heat is equal to C times M times delta T. And it's important that I make sure to put the right pieces of information in here. C is going to be the specific heat capacity, but I must match this with the phase that I am in. Okay, noting here that we've got situations where we've got a solid that we're warming up, and we're going to need to use a specific heat capacity that's unique to a solid. And then we've got liquid, and we didn't take this all the way up, but we could also have a gas. The other thing we need to make sure that we recognize is M stands for quantity, and this is going to be in grams. So if we weren't given something that was in grams, we'd need to do a little bit of a calculation in order to figure that out. Okay. The last thing is dealing with our delta T. Okay. And with our delta T here, again, it doesn't matter if this is in Kelvin or centigrade because we're taking the difference between 2 temperature units, a starting and a final temperature. So it's always final minus initial. The magnitude of that difference is going to be the same whether we have units of Celsius or units of Kelvin. It's just, remember, when we do Kelvin, we just shift everything up so that it's we never have negative numbers. Okay, so again, in this case, it wouldn't matter, but we need to make sure that we are only taking the temperature change of that phase that we are in. So it's only of that single phase. So what do I mean there? I'm never gonna have a difference between 25 and minus 20 because that's overlapping 2 phases, right? My one delta T is gonna be here, and then my other delta T is gonna be here. So let's go ahead and sort of map that on. Let me move this guy over just a little bit so I have some room here. So again, if I'm thinking about this is gonna be one delta T, okay? That's gonna be, let's call that delta T2. That's gonna be for here, delta T2. And then this delta T is going to be for my first delta T, okay? So I know that's a lot, but we have to make sure we match all of these pieces together. So that's if we have one of those increasing lines. Well, what if I have a flat line? A flat line represents I am changing the phase but keeping the temperature the same. So this is a phase change. I'm either doing one of 2 kinds of phase changes. I'm either transitioning between melting and freezing, depending on whether I'm adding or removing heat. And then I'm transitioning between boiling and condensing, again, depending on whether I'm adding or removing heat. Okay, so what do I use for this? Well, I'm going to use an enthalpy parameter. I'm either going to use the delta H of fusion or the delta H of vaporization. Now, again, the delta H of fusion here, this has to do with if you're doing melting or freezing. And then the delta H of vaporization has to do with boiling or condensing. Okay, so how do I use this parameter? Basically, I just take this delta H of fusion. This delta H of fusion is going to have units of kilojoules per mole. Okay, and what I'm going to do is I'm going to multiply it by the number of moles of my substance that I have. So note up here, this was given in terms of grams. So I need to take that number of grams and I need to multiply it by the, or I should say divide by the molecular weight, right? Because I'm going to have the number of grams in terms of the number of moles. That's my molecular weight. And that will give me the number of moles of water or whatever substance we're doing this with, right? So I multiply the number of moles that I have by the kilojoules per mole to do that process, and then I'm going to get an answer in terms of the heat that's required for that phase change. Now, because I had 3 different processes, 3 different times that I was adding heat, adding heat, adding heat, if I want to figure out how much heat's required for the whole process, I add all of those heats up. So once I do, in this case, these 3 different calculations, I'm going to add them all up, and that's going to give me my answer. Okay, so let's go ahead and then try to do those calculations. So let's map on just to this little picture here where we are going, right? We're doing here to here, here to here, and then there to there, right? So we need to now go on and sort of match the pieces of information that we need. So this is all constants, information that you'd be given. You're going to be given all of it. You just need to know what parts to use. Okay, so let's go ahead and do our 3 calculations here. I'm going to have 2 calculations that look like this. When I'm heating up my solid, I'm going to use a specific heat capacity for the solid times the 22.67 grams of my solid times my temperature final minus temperature initial. So my temperature final is 0 minus negative 25 is where I started out. Now again, I need to make sure I use the correct heat capacity here. So I'm going to be using this guy for this first calculation. Okay, so doing all the math for this, it's going to be this 2.09 joules per gram Kelvin times 22.67 times positive 25. My Q is going to be equal to 947.606 joules. Okay, I would leave lots of significant figures as you're working through problems here, round only at the end. I'm going to do a very similar kind of calculation for my liquid. So when I'm heating my liquid between 0 and 25 degrees. So now I'm going to use C for my liquid, my specific heat capacity for liquid, 22.67 grams. I'm not changing the amount that I have. And now my temperature final is going to be, oh, and look what I did here. I apologize. This needs to be, it was at minus 20. My math is right. My number that I put in there is wrong. So now it's going to be 25 is my final minus 0. So when I put in, and let's just kind of highlight and match where I grabbed this, now I'm heating a liquid. So that's why I need to use that guy. You'll notice that the amount that I have didn't change, okay? The delta T did change, and again, I had to use it for the length of the line that I had there. Okay, so now I'm going to put in these values. It's going to be 4.18 joules per gram Kelvin times 22.67 times 25. And notice that 25, even though it might have units of Celsius, I don't add 273 to that, okay? The difference between those 2 temperature values, if I converted them to Kelvin, or the difference if I left them at Celsius, is still 25. So a classic place that students can make mistakes is don't do that conversion to Kelvin after you take the difference. If you wanted to do it beforehand, it's not wrong, it's just extra work. All right, mathematically, this answer is 2,369 joules, okay? Now the last calculation I'm going to need to do a little extra something for. I need to know the number of moles of water that I have. So 22.67 grams of water, the molecular weight of water is 1 mole is 18.01 grams. So I've got 1.2587 moles of water. Now why that's important is I need to use the delta H for this melting process, which is the delta H of fusion. So the delta H of fusion, and I'm going to take that, and that is again 6.01 kilojoules per mole, and I'm going to take that and multiply it by the number of moles that I have. Let me put this so that it's easier to sort of see the unit conversion here. Kilojoules per mole times 1.2587 moles. So again, this number is how I get that guy. And to map on where these pieces come from, I'm using the delta H of fusion, right? So that's this guy right here. Go ahead and highlight that part. Okay. Mathematically, this works out to 7.565 kilojoules. Okay. And now what I need to do is that my heat total is going to be adding all three of these together. Okay. So I'm going to be adding 947.606 plus 23, and let me keep my units in here. I want to make sure we keep our units because I'll have to convert either one to joules or the other one to kilojoules. Actually, let's do it this way. It might be easier. This is the way I did it on my key anyways. I'm going to convert these two to kilojoules because this one's already in kilojoules. Now, unless I specify in the answer, you could do either one. So I'm going to have 0.947606 kilojoules plus 2.369 kilojoules plus 7.565 kilojoules. Add all of those up and you get 10.88 kilojoules of heat is required to take that ice cube out of your freezer and convert it into a liquid puddle on your benchtop. So hopefully that might help for those of you who are a little bit confused still with how this whole process works. Come to problem solving sessions, come see me in office hours if you're still struggling, and we can work through some more.